There's something profoundly unsettling about the notion that everything might already be over. Not in some distant, theoretical future, where stars burn out and galaxies drift into darkness, but right now, at this very moment, as you read these words, as your neurons fire and your heart beats, the universe itself might be in the process of its final transformation. A transformation so subtle, so imperceptible, that we continue our lives completely unaware that the end has already begun. We humans have an extraordinary talent for assuming permanence where none exists. We build our homes as if they'll stand forever. We plan our lives decades in advance. We speak of the future with casual certainty, as though tomorrow is guaranteed by some cosmic contract. But what if this assumption, this bone-deep certainty that the universe will continue much as it is, represents the grandest delusion our species has ever entertained? The question isn't whether the universe will end. Physics has made that answer devastatingly clear. The question is whether it might have already started ending, and we simply lack the perspective to notice. Consider for a moment the nature of endings themselves. When does something truly end? Is it at the final, catastrophic moment of cessation? Or does the ending begin much earlier, in subtle shifts and quiet transitions that only become recognizable in retrospect? A tree doesn't die the moment it falls. It begins dying months or years before, in ways invisible to the casual observer. A star doesn't explode without warning. It spends millennia in a delicate dance with gravity and fusion, each moment bringing it closer to its spectacular finale. Perhaps the universe operates on similar principles. Perhaps what we call the present moment is actually the long, drawn-out process of cosmic dissolution, and we're simply too small, too brief, too embedded within the process itself to recognize it for what it is. This isn't merely philosophical speculation. It's a question that sits at the intersection of cosmology, quantum mechanics, and the fundamental nature of reality itself. And the more we learn about the universe, the more unsettling the possible answers become. Let's begin with what we know. The universe is approximately 13.8 billion years old, born in that primordial explosion we've come to call the Big Bang. For billions of years, it has expanded, cooled, and evolved, giving rise to stars, galaxies, planets, and ultimately, life itself. By any reasonable measure, the universe appears to be in its prime, a vast, dynamic arena of ongoing creation and transformation. But appearances can be deceiving. In the depths of quantum field theory, there exists a concept so fundamentally threatening to everything we take for granted that it seems almost too terrible to contemplate. It's called vacuum decay, and if certain theories are correct, it represents not just a possible end to the universe, but an end that could be spreading through space at this very moment, racing toward us at the speed of light itself. To understand vacuum decay, we need to talk about something called the Higgs field. You might have heard of the Higgs boson, the so-called God particle that physicists discovered at CERN in 2012. But the Higgs boson is just a ripple, a disturbance in something far more fundamental, the Higgs field itself. The Higgs field permeates all of space. It's not something that exists in certain places and not others. It's everywhere, always, an invisible fabric woven into the very structure of reality. And it's the Higgs field that gives particles their mass. Without it, electrons, quarks, and all the other fundamental particles would zip around at the speed of light, unable to form atoms, unable to create the complex structures that make up stars, planets, and people. The Higgs field, in other words, is one of the most essential features of our universe. It's part of what makes our reality the way it is. But here's where things get disturbing. The Higgs field exists in what physicists call a particular state, a configuration of energy. Think of it like a ball resting in a valley between hills. The ball is stable there, content to remain at rest. That valley represents the current state of the Higgs field throughout our universe. The problem is that this valley might not be the lowest possible valley. There might be a deeper one somewhere else on the landscape, a state of lower energy that the Higgs field could theoretically fall into. If that's the case, then the Higgs field throughout our entire universe is in what's called a false vacuum, a state that appears stable but is actually metastable, meaning it could potentially transition to a true lower energy state. And if that transition were to begin anywhere in the universe, if the Higgs field were to suddenly drop into that lower energy state in even a single point in space, the effects would be catastrophic beyond measure. The transition would create a bubble of this new, lower energy vacuum, and that bubble would expand outward at the speed of light, converting the false vacuum into true vacuum as it went. Inside the bubble, the laws of physics would be fundamentally different. Particles would have different masses. Atoms couldn't form in the way they do now. The chemistry that makes life possible would be impossible. Everything, stars, planets, every living thing would be instantly destroyed, not by heat or force, but by the simple fact that the physics required for their existence would no longer apply. And here's the truly terrifying part. We would never see it coming. Because the bubble expands at the speed of light, and light is the fastest way information can travel through the universe, there would be no warning, no advance signal, no time to prepare or react. One moment, everything would be normal. The next moment, well, there wouldn't be a next moment. The transition would be instantaneous from our perspective, a cosmic off switch with no delay between the flipping and the darkness. Somewhere in the universe, right now, such a bubble could already exist. It could have formed 10 billion years ago in a distant galaxy, and it could be racing toward us at this very moment, expanding relentlessly, consuming everything in its path. In the time it takes light from the nearest stars to reach us 4 years, 10 years, 100 years, the bubble could have already travelled unimaginable distances, snuffing out galaxy after galaxy as it goes. And we would never know until the instant it arrived. This is what makes vacuum decay different from other scenarios of cosmic catastrophe. It's not a slow heat death stretching across trillions of years. It's not the gradual dimming of the last stars. It's immediate, absolute, a complete rewriting of reality's source code with no possibility of recovery or survival. But is this actually possible? Or is it just theoretical fear-mongering, an abstract mathematical possibility with no bearing on reality? The honest answer is that we don't know. The stability of the Higgs field depends on extremely precise measurements of particle physics specifically. The exact mass of the Higgs boson itself and the exact mass of the top quark. When physicists at CERN measured these values, they found something deeply unsettling. The measurements place our universe right on the edge between stability and instability. If the values were slightly different, just a tiny bit higher or lower, we could say with confidence that the Higgs field is either stable or definitely unstable. But the actual measurements put us in an ambiguous region, a knife's edge where the field could be stable or it could be metastable, hanging by a quantum thread. Some calculations suggest that the Higgs field is indeed metastable, meaning our universe exists in this false vacuum state. But they also suggest something somewhat reassuring. Even if the field is metastable, the probability of it spontaneously transitioning to true vacuum is vanishingly small. The universe would need to exist for timescales far longer than its current age, perhaps 10 to the power of several hundred years, before such a transition would become likely. But there's a catch. That calculation assumes nothing else disturbs the field. It assumes the universe continues along peacefully, with nothing triggering the transition. Quantum field theory tells us that vacuum isn't really empty. It's seething with virtual particles, with quantum fluctuations, with energy appearing and disappearing on timescales too brief to measure directly. And under certain extreme conditions, in the intense gravity near a black hole, or in the phenomenal energy densities that might exist in the cores of colliding neutron stars, or in the aftermath of the Big Bang itself, these fluctuations could become large enough to trigger the transition. Some physicists have suggested that cosmic rays' high-energy particles that constantly bombard Earth from space could theoretically carry enough energy to create a bubble of true vacuum. If that were possible, the fact that we're still here, after billions of years of cosmic ray bombardment, would suggest the Higgs field is actually stable after all. But others point out that we might simply be lucky, or that the energies required might be higher than anything cosmic rays can provide, or that the process might require specific conditions we haven't encountered yet. The truth is, we're performing calculations at the very edge of our theoretical understanding, trying to predict the behavior of fields and particles in regimes we can barely imagine, let alone test experimentally. We're reading tea leaves made of quantum probabilities and hoping we're interpreting the patterns correctly. And that uncertainty is itself unsettling. We've built our entire civilization, our entire understanding of our place in the cosmos, on the assumption that the laws of physics are stable and reliable, that the universe operates according to consistent principles that we can discover and understand. The possibility of vacuum decay challenges that assumption at its foundation. It suggests that the universe itself might be unstable at a fundamental level, that existence itself might be contingent and temporary in ways we've never fully appreciated. But vacuum decay is just one possible ending, one scenario among several. To truly understand whether the universe is already ending, we need to look at the bigger picture, at the large-scale structure and fate of the cosmos itself. This is where we encounter one of the most profound discoveries in the history of science, a discovery so unexpected, so contrary to all theoretical predictions, that it forced physicists to completely reconsider their understanding of the universe. In the late 1990s, two teams of astronomers were studying distant supernovae, exploding stars so bright they can briefly outshine entire galaxies. These particular supernovae, called type Ia supernovae, are special because they always explode with roughly the same brightness. This makes them useful as standard candles, cosmic measuring sticks that allow astronomers to determine distances across the universe. Both teams were using these supernovae to measure how fast the universe was expanding, and more importantly, how that expansion rate was changing over time. The prevailing assumption was that gravity would be slowing the expansion down. After all, every galaxy is gravitationally attracted to every other galaxy, and that attraction should act as a brake on the cosmic expansion, gradually slowing it over billions of years. The question both teams hoped to answer was just how much the expansion was slowing down. Would it slow enough to eventually stop and reverse, causing the universe to collapse back on itself in a cosmic crunch? Or would it slow down forever, but never quite stop, leading to an eternal but decelerating expansion? What they discovered was neither of these options. The universe wasn't slowing down at all. It was speeding up. The expansion of the universe, the rate at which galaxies are moving away from each other, was accelerating. Somehow, Despite all the matter and energy pulling everything together through gravity, space itself was expanding faster and faster. This discovery won the leaders of both teams the Nobel Prize in Physics in 2011, but it also opened up one of the deepest mysteries in modern cosmology. What could possibly be driving this acceleration? The answer, or at least the name we've given to our ignorance, is dark energy. And dark energy is by far the most abundant thing in the universe. When we take inventory of everything in the cosmos, all the matter and energy we can detect and measure, we find something shocking. Normal matter, the stuff that makes up stars, planets, and people, accounts for less than 5% of the total. Another 27% or so is dark matter, a mysterious substance that doesn't interact with light but does exert gravitational influence. The remaining 68% of the universe is dark energy. Nearly 7/10 of everything that exists is this strange, invisible energy that permeates space itself and drives the accelerating expansion of the universe. We don't know what dark energy is. We don't know where it comes from. We don't fully understand its properties or how it behaves. What we do know is that it's causing the universe to expand faster and faster, driving galaxies apart at an ever-increasing rate. And this acceleration has profound implications for the far future of the cosmos. Implications that suggest the universe might be heading toward an end so absolute, so final, that it makes vacuum decay look almost merciful by comparison. As the universe continues to expand and the acceleration continues, something remarkable happens. The distance between galaxy clusters grows faster and faster. Eventually, the expansion becomes so rapid that distant galaxies begin moving away from us faster than the speed of light. This doesn't violate relativity, by the way. Nothing is moving through space faster than light. It's space itself that's expanding, but the effect is the same. Light from those distant galaxies will never reach us. They cross what's called the cosmic event horizon, disappearing from view forever. As billions of years pass, more and more of the universe will cross this horizon. Nearby galaxy clusters, gravitationally bound to each other, will remain visible, but everything else, every distant galaxy, every far-flung quasar, every structure beyond our local group, will fade from view, their light stretched into invisibility by the expanding space between us. Eventually, in the far future, an observer in our galaxy, assuming anything remains to observe, would look out at the universe and see almost nothing. The night sky would be nearly empty, containing only the gravitationally bound galaxies in our local group and nothing beyond. The vast cosmic web of galaxies that stretches across the observable universe today would have disappeared beyond the horizon, leaving behind a small island of matter in an ocean of empty space. But that's just the beginning. As dark energy continues to dominate and the expansion continues to accelerate, even those nearby structures won't remain. The acceleration will eventually grow strong enough to overcome the gravitational binding of galaxy clusters, pulling them apart. Then it will tear apart individual galaxies, sending their stars flying into the void. Then it will rip apart solar systems, then planets, then atoms themselves. This is called the Big Rip, and it represents one possible, ultimate fate of the universe. A fate in which the fundamental forces holding matter together are overwhelmed by the accelerating expansion of space itself. In this scenario, the universe doesn't end in fire or ice. It doesn't fade gently into darkness. It tears itself apart at every scale, from the cosmic to the quantum, until nothing remains but isolated particles scattered across space, unable to interact, unable to form structures, unable to generate anything resembling order or complexity. The timeline for the Big Rip depends on the exact properties of dark energy, particularly on something called the equation of state parameter. If dark energy remains constant forever, if it maintains the same density even as space expands, then the Big Rip won't happen. The universe will expand forever, but matter won't be torn apart. But if dark energy becomes more intense over time, if its density increases, or if its negative pressure grows stronger, then the Big Rip becomes inevitable. And current observations aren't precise enough to rule out this possibility. Some calculations suggest the Big Rip could happen in as little as 20 billion years, less than twice the current age of the universe. Others place it much farther in the future, or suggest it won't happen at all. We simply don't know enough about dark energy to say with certainty. But here's what we do know. The universe is already in the process of this transformation. The acceleration has been going on for billions of years. Galaxies are already receding from us at increasing speeds. The cosmic event horizon is already closing in, cutting us off from ever larger portions of the universe. If you want to argue that the universe has already begun its ending, that we're living in the opening act of the final chapter, the accelerating expansion driven by dark energy provides compelling evidence. We're watching the universe empty out around us, watching the cosmic horizon contract, watching the future narrow into a progressively more isolated and dark existence. The process is slow by human standards, but it's inexorable. Already, there are galaxies that exist beyond our cosmic event horizon, places in the universe we will never be able to see or reach, no matter how long we wait or how fast we travel. Information about those regions is forever lost to us, severed by the expansion of space itself. In a very real sense, parts of the universe have already ended for us. They still exist, but they might as well not, because we can never interact with them, never receive information from them, never know what happens there. They've crossed a boundary from which there is no return, and that boundary is getting closer. Every day, more of the universe slips beyond the cosmic event horizon. More galaxies vanish from the realm of things we could ever possibly reach. More of reality becomes irretrievably inaccessible. If the universe is a book, pages are being torn out one by one before we've had a chance to read them. If it's a symphony, notes are fading into silence before we can hear them. If it's a vast repository of information and possibility, sections of it are being locked away forever, the keys thrown into an abyss. This raises a question that seems almost philosophical, but has genuine physical implications. In what sense does a part of the universe exist if it can never interact with us, never exchange information with us, never influence our region of space in any way? From our perspective, functionally, those regions might as well not exist at all. They're as inaccessible as a universe before the Big Bang, or a universe beyond the multiverse. They've crossed the event horizon not into a black hole, but into permanent cosmic isolation. And this is happening constantly, silently, invisibly. The universe is hemorrhaging information and possibility, and there's nothing we can do to stop it. Some physicists have tried to find solace in the fact that this process is slow, that we have billions of years before it becomes a practical concern, that countless generations of stars will be born and die before the universe becomes truly isolated and empty. But billions of years, in cosmic terms, is nothing. The universe existed for billions of years before Earth formed. It existed for billions of years before life arose. From the perspective of cosmic time, the accelerating expansion began relatively recently, only about 5 billion years ago, when dark energy's influence overtook the gravitational attraction of matter. We're living in a transitional period, a moment when the universe is shifting from one regime to another, From a past dominated by matter and gravity, where structure formed and complexity emerged, to a future dominated by dark energy and expansion, where structure dissolves and isolation prevails. We're living, in other words, in the twilight of the universe's era of structure and complexity. The peak has already passed. The trajectory is already set. Everything from here on is diminishment and decay, spread out across timescales so vast they seem infinite from our limited perspective, but which are finite nonetheless. This isn't speculation or theoretical possibility. This is the universe we live in, based on observations and measurements that grow more precise with each passing year. The accelerating expansion is real. Dark energy is real. The cosmic event horizon is real. The future, it implies, a future of increasing isolation and eventual dissolution, is the most likely outcome given everything we currently understand about cosmology. But there's another layer to this story, another way in which the universe might already be ending that has nothing to do with dark energy or vacuum decay or the large-scale structure of space-time. It has to do with information. The concept of information in physics has undergone a remarkable transformation over the past century. Once considered something abstract and separate from physical reality, something that described reality but wasn't part of it, information has increasingly come to be understood as fundamental to the universe itself. This shift began with quantum mechanics, which revealed that the act of measurement, of gaining information about a system, fundamentally affects that system's state. It continued with information theory, which showed that information has thermodynamic properties and can be treated as a physical quantity. And it reached a kind of culmination with black hole thermodynamics, which demonstrated that information and entropy are intimately connected to the geometry of space-time itself. Today, many physicists believe that information isn't just a description of reality, it is reality. That, at the deepest level, the universe is made not of matter or energy or even space-time, but of information. Physical processes are information processes. The evolution of the universe is the evolution of information. If this view is correct, then the fate of the universe is intimately tied to the fate of information. And here we encounter something deeply disturbing. According to our best current understanding of thermodynamics and black holes, information can be destroyed. The destruction of information is intimately connected to one of the most fundamental laws in physics, the second law of thermodynamics. This law states that in any closed system, entropy, a measure of disorder or randomness, always increases over time. Order inevitably gives way to disorder. Structure inevitably breaks down into chaos. Hot things cool, concentrated energy disperses, complex systems decay into simpler ones. This isn't just a tendency or a statistical preference. It's one of the most ironclad laws we've discovered, a principle that has never been observed to be violated. The arrow of time itself, the fact that we experience time as flowing in one direction rather than another, is thought to be a consequence of increasing entropy. And here's the connection to information. Entropy and information are inversely related. High entropy means low information. When you maximize disorder, you minimize meaningful structure, meaningful patterns, meaningful information content. Every physical process that increases entropy, therefore, destroys information. When you burn a book, the information contained in its pages is converted into heat and smoke and ash, a state of higher entropy and lower information content. The information isn't truly gone in some absolute sense. In principle, if you knew the exact position and velocity of every particle of smoke and ash, you could reconstruct the book. But, in practice, that information has become irretrievably scrambled, effectively destroyed. Now scale this up to the entire universe. The universe began in a state of extremely low entropy. The Big Bang was an incredibly ordered, structured state, despite being unimaginably hot and dense. All the matter and energy in the universe was concentrated in a tiny region, described by relatively simple initial conditions. In information-theoretic terms, it took very little information to completely specify the state of the early universe. Since then, entropy has been increasing. Stars have formed and burned. Galaxies have evolved. Complex structures have emerged and dissolved. And with each passing moment, the total entropy of the universe increases, while the total meaningful information content arguably decreases. Eventually, if current projections hold, the universe will reach a state of maximum entropy. This is called heat death, a state where all energy is evenly distributed throughout space, where no temperature differences exist, where no work can be done, where nothing changes anymore, because there's no gradient, no difference, no structure left to support change. In this state, the universe still exists. There's still space, still particles, still energy. But there's no information worth speaking of. Everything is uniform, homogeneous, featureless. The universe has become a vast, cold, dead expanse where nothing happens, nothing can happen, because there's no structure left to enable happening. Some physicists describe this as a state where the universe has forgotten everything. All the information about stars and galaxies, about planets and life, about the intricate history of cosmic evolution, all of it has been erased, scrambled into thermal noise, converted into the meaningless random motion of particles. The timeline for heat death is staggering far longer than the timeline for the Big Rip or even the evaporation of black holes. We're talking about 10 to the power of 100 years or more, timescales so vast that our human minds cannot truly comprehend them. But the process has already begun. Entropy is already increasing. Information is already being destroyed, converted into heat and disorder, with every physical process that occurs. Every time a star fuses hydrogen into helium, entropy increases. Every time energy radiates into space, entropy increases. Every time any irreversible process occurs anywhere in the universe, entropy increases and information is lost. We're living in a universe that is actively forgetting itself, slowly but inexorably erasing the record of its own history, converting structure and meaning into noise and randomness. And once again, we find ourselves asking, in what sense is this not already an ending? If the essence of existence is information, structure, complexity, and meaning, then a universe that is steadily losing all of those things is a universe in the process of ending, regardless of how much time the process takes. We tend to think of endings as sudden and dramatic explosions, collapses, catastrophic failures. But the universe seems to favour a different kind of ending, a slow dissolution, a gradual fading, a long goodbye that stretches across timescales so vast that any individual moment seems unchanging, even as the overall trajectory leads inexorably toward oblivion. This brings us to perhaps the most unsettling implication of all, the possibility that we're living in what might be the only era in cosmic history where beings like us, conscious, intelligent, capable of understanding the universe, can exist at all. The universe is 13.8 billion years old. Stars have been forming for most of that time, creating the heavy elements necessary for planets and life. Earth formed about 4.5 billion years ago. Life arose relatively quickly after that. Complex multicellular life took longer, about 3 billion years. Intelligent, technological civilization emerged only in the last few thousand years. This seems like a long time, but compared to the full lifetime of the universe, it's the blink of an eye. We arrived on the scene relatively early in cosmic history. There will be stars forming for trillions of years to come. There will be habitable planets for just as long. In principle, there's no reason intelligence and consciousness couldn't emerge again and again, countless times throughout that vast future. But there's a problem with this assumption, and it has to do with the increasing entropy and the effects of dark energy we discussed earlier. As the universe continues to expand and age, several things happen that make the emergence of complexity increasingly difficult. First, the raw materials for making stars' hydrogen and helium get locked up in stars and stellar remnants, becoming less available for forming new stars. Second, the overall metallicity of the universe increases, but the rate of star formation decreases. Third, as dark energy continues to dominate, the universe becomes increasingly spread out and isolated, making it harder for gravitational collapse to create dense regions where complexity can emerge. There's also the simple thermodynamic argument. As entropy increases, the universe moves toward equilibrium. And equilibrium is the enemy of complexity. Life, consciousness, intelligence, all of these require being far from equilibrium, require energy gradients and structure, and organized complexity that becomes harder to maintain as the universe ages. Some physicists have calculated that we might be living in a special window, a relatively brief period in cosmic history where the conditions are right for complex structures like galaxies, stars, planets, and life to form and persist. Before this window, the universe was too hot, too dense, too chaotic. After this window, perhaps only a few trillion years from now, the universe will be too cold, too sparse, too close to equilibrium. We arrived during the window. We evolved during the window. We developed the capacity to understand the universe during the window. But the window is closing. Future observers, if any exist, might find themselves in a universe that looks nothing like ours. A universe where the night sky is almost empty, where stars are rare and dying, where the cosmic microwave background has cooled to near absolute zero, where the evidence of the Big Bang and cosmic evolution has faded beyond detection. They might look out at their universe and conclude it has always been essentially the way it is: small, isolated, eternal, and unchanging. They would have no way of knowing about the vast cosmic web that existed billions of years before them, about the era of star formation and galaxy evolution, about the rich, complex history that preceded their existence. In a very real sense, the universe would have ended for them, not in the sense of ceasing to exist, but in the sense that the universe as arena of structure, evolution, and possibility would be over. They would be living in the aftermath, in the long, slow decline toward final equilibrium. And here's the truly unsettling question. How do we know we're not already those future observers? How do we know the peak of cosmic complexity isn't already behind us, that we're not already living in the decline, in the long fade toward heat death? The evidence, admittedly, suggests we're not. We still see abundant star formation. The universe is still rich with structure and activity. The cosmic microwave background still provides clear evidence of the Big Bang. But the transition from peak to decline isn't sharp. There's no single moment when the universe shifts from vibrant to dying. It's a gradual change, a slow turning of the cosmic tide. And by the time it becomes obvious, by the time the decline is unmistakable, it will have been underway for billions of years. We might be living at the beginning of that decline. The acceleration of expansion began only 5 billion years ago. The rate of star formation in the universe peaked about 10 billion years ago and has been declining ever since. The density of matter in the universe is lower now than it's ever been and continues to decrease. By many measures, the universe has already passed its prime. It's already in the phase of dissolution and decay. The process is slow, but it's underway, and this raises profound questions about meaning and purpose. If we're living in a universe that is actively ending, if everything we are and do is occurring against the backdrop of irreversible cosmic decline, what does that mean for how we should think about our existence? One response is nihilism, the conclusion that nothing matters if it's all going to end anyway. If the universe is dying, if entropy is increasing, if eventually everything will be erased, then why does any of it matter? Why care about anything when the ultimate outcome is oblivion? But this response, while emotionally understandable, is philosophically shallow. The fact that something is temporary doesn't make it meaningless. The fact that a symphony ends doesn't make the music meaningless while it plays. The fact that a flower wilts doesn't make its beauty meaningless while it blooms. In fact, one could argue the opposite, that temporality is what gives things meaning, that the finite, limited nature of existence is precisely what makes each moment valuable, what makes each choice significant, what makes consciousness and experience precious. If the universe is indeed in the process of ending, if we're living in a brief window of complexity and possibility within the vast cosmic timeline, then we're witnesses to something extraordinary. We're the universe become aware of itself, contemplating its own nature and fate, creating meaning and beauty and understanding in the midst of encroaching entropy. There's something defiant about consciousness in a dying universe. Something brave about seeking truth and creating art, and loving each other when the cosmos itself seems indifferent to our existence. When the laws of physics guarantee that everything we build will eventually crumble, everything we know will eventually be forgotten. But perhaps that's the point. Perhaps meaning doesn't come from the universe or its ultimate fate. Perhaps meaning is something we create, something we generate through our choices and connections and commitments, something that exists because we make it exist, not because it's written into the fabric of reality. The universe may be ending. It may have been ending for billions of years. It may continue ending for trillions more. But here, now, in this brief window of structure and complexity, we exist. We think. We feel. We understand. We create. We matter to each other. And maybe that's enough. There's also another perspective worth considering, one that emerges from the strange implications of quantum mechanics and the nature of observation itself. In quantum mechanics, the state of a system isn't definite until it's measured or observed. Before observation, the system exists in a superposition of all possible states, described by a wave function. Only when observation occurs does the wave function collapse into a definite state. This has led some physicists and philosophers to suggest that observation, consciousness, measurement, whatever you want to call it, plays a fundamental role in bringing reality into existence. That in some sense, the universe requires observers to be fully real. If this view has any validity, then the existence of consciousness and intelligence in the universe isn't just an accident or a side effect of physical processes. It's an integral part of what makes the universe actual, rather than merely potential. And if that's true, then the era of consciousness, the window we're living in, where the universe can observe itself, might be special in a fundamental way. Not just biologically or historically special, but ontologically special. The universe becomes fully real through being observed and understood. When consciousness ends, when the last star dies and the last observer fades into darkness, the universe doesn't just become empty and cold. It becomes, in some sense, less real. It returns to a state of pure potentiality, of unrealized possibility, of wave functions that never collapse because there's no one left to collapse them. This is highly speculative, of course. The role of consciousness in quantum mechanics is deeply controversial and far from resolved, but it offers an interesting perspective on why the ending of the universe might matter in ways beyond just the physical dissipation of energy and structure. We might be living during the brief period when the universe is maximally real, maximally actualized through observation and understanding. And the ending that's underway might be not just a physical ending, but an ontological one, a gradual return from actuality to mere possibility. Let's return to the question we started with. Is the universe already ending? The answer depends on what we mean by ending. If we mean in the process of transitioning from one state to another, where the final state is radically different from the current one, then yes, absolutely, the universe is ending. It has been for billions of years. The acceleration of expansion, the increase in entropy, the gradual dissipation of structure and energy, these are all ongoing processes that will eventually lead to a universe that looks nothing like the one we inhabit today. If we mean approaching a state where complexity and structure become impossible, then the answer is also yes, though the timeline is much longer. Heat death, the Big Rip, maximum entropy, all of these represent states where the universe, as a dynamic, evolving, complex system, ceases to exist, even if space and particles and energy still remain. If we mean in danger of sudden, catastrophic destruction through vacuum decay, then the answer is maybe. We don't know enough about the stability of the Higgs field to say with certainty, but the possibility exists, and if it's happening, we wouldn't know until the instant it reached us. But here's what we can say with confidence. We're living in a transitional period. The universe has passed its peak of star formation, its peak of matter density, its peak of gravitational binding. We're on the downward slope now, in the long decline toward whatever final state awaits. This isn't cause for despair, but it is cause for perspective. We're not living in a static, eternal cosmos. We're living in a dynamic, evolving, and yes, dying universe. Everything around us, the stars, the galaxies, the very laws of physics that allow complexity to exist, is temporary. Precious, because it's temporary. Meaningful, because it's fleeting. The universe is already ending, has been ending, will continue ending. But here, now, in this moment, it's also alive, still creating, still evolving, still giving rise to new structures, new possibilities, new instances of consciousness, contemplating the cosmos. We're witnesses to both the ending and the ongoing existence, the decline and the vibrancy, the mortality and the life of the universe. We stand at a unique vantage point in cosmic history, late enough to understand what's happening, early enough to still witness structure and complexity, aware enough to contemplate our own cosmic context. The universe is ending, but it's not over yet, and in the vast gulf between those two statements lies everything that matters, every star that still burns, every world that still harbours life, every mind that still seeks to understand, every heart that still loves, every moment of consciousness that still illuminates a small corner of reality. The ending is real. The process is underway. The outcome is inevitable, given enough time. But here we are, still asking questions, still seeking answers, still creating meaning in the face of cosmic indifference, still alive in a universe that won't be alive forever, making the most of the brief window we've been given. Perhaps that's the real answer to whether the universe is already ending. It's both ending and not ending, dying and still vibrantly alive, racing toward oblivion and still teeming with possibility. The ending is built into the structure of reality itself, written into the laws of thermodynamics and the properties of dark energy. But so is the capacity for structure, complexity, life, and consciousness. For a while, perhaps a brief while in cosmic terms, but our while, nonetheless, the universe supports beings who can understand it, appreciate it, find meaning in it. The ending will come. In one form or another, sooner or later, the universe as we know it will cease to exist. But that ending, whenever and however it arrives, won't erase the fact that, for a time, the universe was home to conscious beings who looked up at the stars and wondered, who asked questions about their cosmic origins and fate, who created beauty and sought truth and loved each other in the midst of the void. That mattered. That matters now. That will have mattered even when the ending finally comes and there's no one left to remember. The universe is already ending, but it's also still beginning, still unfolding, still becoming. And we're here to witness both at once the mortality and the vitality, the decline and the wonder, the ending and the miraculous fact that there's still something rather than nothing, still consciousness rather than darkness, still meaning in a cosmos that has no obligation to provide any. We stand in the twilight of cosmic history, watching the long sunset of structure and complexity, knowing that night is coming but not yet here. And in that knowledge, in that awareness of our place in the vast arc of cosmic time, we find both humility and significance. The universe is ending. Long may it last.